Okay, chapter 9 is on testing or whatever, introduction to statistical tests. And the tests we're kind of talking about here are called hypothesis tests. Hypothesis testing is to make decisions concerning the value of a parameter. Remember, a parameter comes from the population, so we're talking about mu, or maybe standard deviation, or p. Our null hypothesis, which is always h with a little zero below it, h naught, is a working hypothesis about the population parameter in question, historical value claim, production specifications, statement that is under investigation or being tested at either a no effect, no difference, or that things that haven't changed. I kind of think of it like this. Maybe you've seen on a commercial, and it says that 75% of doctors believe that a physical yearly will prolong your life by 10 years. Okay, so the average lifespan is extended by 10 years. That would be like the null hypothesis. What we're going to do is kind of test that null hypothesis with an alternative hypothesis. Any hypothesis that is different from the null hypothesis, the statement that you adopt should be, you should decide to reject that null hypothesis. That's with an h with a little 1. So example here, I got the speed limit is 65 miles per hour in U.S. highways. So my null hypothesis is going to be mu equals 65. I believe people speed, so my alternative hypothesis would be that mu is bigger than 65. Okay, so null the accepted, alternative is something I believe to be true. Now, here we go. We've got this manufacturer's claim that the light bulb will burn on average of 1,000 hours. So the null hypothesis would be that the population length of that light bulb burning is 1,000 hours. We have reason to believe that it does not last that long. Now, I could test greater than less than. I can also test that, maybe it just is different than that null hypothesis. We'll talk about the different types of tests as we kind of work through this and get through this in the next couple of weeks. So some errors in testing. So what could possibly go wrong with testing? Well, a type 1 error is that I reject the null hypothesis when it's actually true. So the null hypothesis before was that people actually do drive 65 miles per hour, but my data believes to say, nope, throw that out. But oops, I just threw out the correct answer. That's a type 1 error. A type 2 error is not rejecting the null hypothesis when it's actually false. So I got this null hypothesis again of 65 miles per hour, but I'm going to hold on to it even though the data tells me to get rid of it. So that's a type 2 error. We're going to test ours on type 1 error. Type 2 errors are a totally different thing. So you can look through this chart in a decision. Do not reject the null hypothesis or reject it. Let's say the null hypothesis is actually true. The correct decision has a probability of 1 minus. This Greek letter is small lowercase a. It's called alpha. Type 1 error is measured in alpha. So let's say alpha is at 5%. This area here would be 95%. Where null hypothesis is false, we got a type 2 error. That's beta. You can look farther into the book. We're not going to get to beta throughout the year, but just something to kind of look at and think about into the future. So let's say here again, we got a hypothesis test here that we want to test. We always have to test it against some sort of level of significance, and you might see me abbreviate it just LS. That's your alpha. It's typically 0.01 or as a percent, 1% level of significance. Fast food restaurant indicates that the average age of its job applicants is 15 years old. So they believe that it's 15 years old. We have suspected that the true age is lower than 15. So we're going to test the null hypothesis is less than 15. Okay. Now, how you'd go about actually test that hypothesis, you need to get some data. And we'll talk about that data here shortly. We have two types of tests where we believe the null hypothesis is different from the alternative hypothesis. That means if it's too low or too big. Okay, so that's a two-tail. And that's kind of the way I think of it is you have the low that's the outlier area, you got the upper that's the outlier area, so you got two possible tails to reject that null hypothesis. We have left tail where the null hypothesis is smaller than that. Left tail, so we have an outlier to the lower part of the normal curve. Or we've got a right tail, which is on the upper part of the normal curve. Now, left tail, right tail kind of helps you out when you're finding out which area you're going to use underneath that curve. This p-value, p standing for probability. Okay, this probability value, you assuming that the null hypothesis is true, the probability that the test statistic will take on values as extreme or more extreme than the observed test statistic. So basically, if we get data that says that, whoa, we're way off, or we're way, way, way off, we would say something about that null hypothesis, and we would do that by getting a smaller, or getting a p-value. Now, the smaller the p-value, the stronger chance that there's evidence against this H0. And by a smaller p-value, I really mean a really small area underneath the normal curve. Okay, so by test statistic, they're talking about finding a z-score. That's if we got the population standard deviation known. When we also have to know, that x follows the normal distribution, or maybe our sample is big enough to assume it follows the normal distribution. We're going to take our average that we found from maybe our collection of data. We've got our null hypothesis mean that we're going to use. We've got our standard deviation, and then n is how big our samples were to collect this mean. We are going to make two conclusions. When your p-value is smaller than that alpha, we'll reject the null hypothesis. The data are statistically significant at the level of sigma, so it kind of varies on what you're testing it against, and that's kind of a known value within the problem. If your p-value is greater than alpha, then we're not going to reject the null hypothesis. We're not necessarily going to say we're going to be correct. We're just going to say we're not going to reject the null hypothesis. So suppose we've got Sam here, who has always been a .25 career hitter in baseball. He works hard during the off season, improves his batting average. He improves to the point that he believes that he can now bat .333. So he thinks that there's going to be an improvement. So his batting average is going to go up. His manager is willing to let him take the third spot in the batting order if he can prove that this new batting average will stay put in the 30 at bats. So based on the practice observation, we know that standard deviation of his getting hit is 0.2. Construct a statistical test to examine the claim that Sam's batting average has improved. So improve, again, meaning that it went up. And we're going to test that at a level of significance of 5%, or 0.05. So we need to identify a null hypothesis. So from the past, the accepted average is 0.250. We believe it's going to improve, or he believes it's going to improve. So mu is now greater than 0.250. Okay, notice how these are all centered around that. My test statistic is going to be a z-score before I get too carried away. My level of significance that I'm going to test this against, or my alpha, is 0.05. So z is going to be the average that he believes he can get, so 0.33. Okay, minus the accepted one, so minus the 0.25, divided by the standard deviation divided by the square root of. Now he's going to hit 30 times, so that's going to be your n. And try to keep the Greek symbols next to each of these numbers so you can kind of grasp as to where I'm getting those from. So in the numerator, I got 0.333 minus 0.25. We got 0.083 in the numerator. 0.2 divided by the square root of 30. So 0.036 or 365. Again, the more decimals you carry, the better. And I get a test statistic, or a z-score, of 2.27. Now, how that's going to help me is I'm going to look in the back of the book, and I am going to find the area underneath the curve that is associated with the z-score of 2.27. Now, in that curve, though, I want to make sure I get my correct area. So there's my 2.27. The book's going to give me the area to the right. So give me a second, I'll look that up real quick. 2.27. 0.9884. Okay? But because it's greater than, I've got a right-tailed test. So the area I actually want is right there. So I'm going to go 1 minus that 0.9884. And get an error 0.0116. That right there is my p-value. Now I'm going to take the 0.0116, I'm going to compare it to 0.05. Okay, and since that's smaller than 0.05, I look back. Here's my comparisons here. So if p-value is smaller than alpha, we're going to, at a 5% level of significance, we reject the batting average of 0.250, and we believe he has improved off of these 30 at-bats. That doesn't necessarily mean that he actually has improved. It just means that the 333 average that he got from those 20 at-bats is enough to, right now, currently say he's improved. So you kind of have to be careful of that. We're not definitely saying he's better than 0.25 now overall for his population. He just means in this very instance he will. Okay, so the EPA, the Environmental Protection Agency, has been studying ammonia nitrogen concentrations, in a river. For many years, the concentration was 2.3 milligrams per liter. So, null hypothesis of 2.3 milligrams per liter. New golf course and housing usage has kind of changed that, either increasing or decreasing. So, we don't care either way. So, we'll test that it's different than 2.3. Right, we've got our population standard deviation of 0.3. Random sample of 8 samples, or 8 water tests, will give you the following results. So what I'm going to have to do is I'm going to have to come up with a sample mean. So I'm going to quickly type into L1 my 2.1, 2.5, 2.2, 2.8, 3, 2.2, 2.4. I'm going to run one of our stats on these. And I get a standard deviation of, a mean of 2.5, maybe 1. Okay, so my test statistic, and again, level of significance, better identify that. I got 0.01. It's different, so I got to find my test stat. So we'll go z equals, okay, 2.51 minus 2.3 divided by your standard deviation of 0.3 and the square root of, here's your 8 that you grab that from. So 2.51 minus, so 0.21, 0.3 divided by 0. I get a z-score of 1.97. Now I'm going to draw that all. I better round that up to the nearest hundredth. Draw myself a little normal curve. Now it's not equals to, so that means I've got two-tailed. So I can look up 1.98 and do the whole 1 minus thing, or I can use symmetry and look up negative 1.98. And I'm going to do that. And that negative 1.98 is going to tell me the area to the left of that z-score. Negative 1.98, 0239 is that guy. But there's also an 0239 there, so I can add those together or double that. So 0.0239 times 2, and my p-value is 0.0478. And now, be careful, I'm comparing that to a different p-value. I'm comparing it down to 1%. So now it's bigger than that. So I would say at a 1% level of significance, we can say that the mean of 2.3 milligrams per liter has changed. Now, that doesn't mean that it has for sure the population mean that is. That just means this particular sample of 8 could change it. Now, if we would have changed this 0.01 to 0.05 for alpha, whole different result. Now I fail to reject that. In fact, like 1% rejection means 99% keeping it around. Okay, so be careful, fail to reject, not accept. We fail to reject the null hypothesis with the understanding that we have not proved it to be true beyond all doubt. Reject, we choose the alternative hypothesis with the understanding that we might not have proved it to be true beyond all doubt either. So it's kind of a, we think you're wrong, but we can't quite say we're right. We just got some information or data right now to kind of take care of that. So here we go, page 494, 1 through 5, 7, 9, 11, and 13. A lot of odds there. You can check those out. Again, I strongly suggest doing a lot of this. This is maybe something that you might want to practice now because it's going to be very similar throughout the rest of the chapter.